In this section of the course, we're going to introduce x86 platform assembly language for 32-bit Intel architecture, and we will discuss the entire assembly process using assembler, putting together a project to be able to invoke assembler and link the program and execute it. We'll familiarize with some basic concepts of assembler. But before we start this conversation, first I'd like to complete the next laboratory exercise, which is introducing a new type of circuitry, and it's called Magnitude Comparator. Magnitude means that it's going to be able to compare unsigned numbers. In our prior laboratories, we've designed a fully featured adder-subtractor device that was also able to indicate an overflow condition for both signed and unsigned results. So this time we're going to leverage our knowledge that we gained from building this circuitry to transition to a different type of device, which just, instead of doing math, actually compares the two inputs. We're still going to base our circuitry on a 4-bit data types. We're going to supply 4 lines for 2 inputs X and Y, or A and B, and then build a circuitry which will compare these 2 inputs as unsigned numbers, and then provide the results such as whether the X is less than Y, equals to Y, or greater than Y. So we're going to create a device with 3 outputs that will indicate these 3 conditions. So obviously you can imagine that when you're trying to build a logic in your code, there has to be a lot of comparisons taking place, and all Boolean expressions, and also expressions involving comparing numbers may have to rely on such devices, this Magnitude Comparator. I have already opened my DigitalWorks environment, and I want you to follow my steps and submit all circuits that you built during this exercise, and this will be your target to complete this laboratory exercise, which is laboratory 5. So prior to the comparator design, let's take a look at some ideas that we could use in this laboratory. I have some notes posted here on this week's set of topics, and this is the notes that are specific to this circuit design. So what we have here is that an idea is that if you add 2 numbers, one is a certain value, and like this, right? This is a binary number, and this is just an unsigned numbers, just bit combinations. And if you flip its bits, and this way you add y plus not y, if we add them as usual, you have a result that all of the bits of this addition are set to 1, because it's always going to be 0, 1 or 1, 0, and the result will be all ones set together. If we continue this thinking, this extra bit right here could be represented as 2 raised to the nth power, where n is the number of bits, because we begin with 2 raised to the 0th power, 1st power, 2nd power, which corresponds to positions of bits 0, 1, 2, and 3, and so that would be the 4th position. So this would give us this idea. So this value, which corresponds to this binary number with 1 at the highest bit set and all zeros, can be expressed as 2 raised to the nth power, where n is the number of these digits right here. Then, interestingly, if we subtract 1 from this value, okay, it would set all bits to n-bit data type of this n-bit data type to 1. Essentially, 2 raised to the nth power minus 1 should give us effectively should give us this value of all bits set to 1 in a data type that has 4, in our example, 4 bits. So this is good. Then we can rewrite this as this, right? So this result is, we already discovered that this has all ones, because we just talked about addition of individual bits, and now we can rewrite it as this equation. So we have the left and right sides equal to one another, and then we can express y as this minus not y, and this could help us to find the condition where x greater than y is true. Okay, so we can discover this outcome. So say that we start with this comparison, and of course x minus y greater than 0. Then we replace y with this equivalent, because we already figured out what it could be rewritten as. So x minus this, then we open the parentheses, we simplify this notation, and now we can take x plus not y should be greater than, if we move to the right hand side, 2 raised to the nth power minus 1. We can transition to this equation, and then we can say that x plus not y is greater than this value, right? So we have we already know that this should be equal all ones in the binary number, and therefore if we just add 1 to this and we get this, right? So 1, 1, 1, 1 plus 1 becomes this value. So that should be greater than or equal x plus not y. So since extra bit is the carry, okay, so we can use the carry flag when we do our additions. And since extra bit is the carry, then carry flag equals 1 signals that x is greater than y. And this is really in situations where we're just talking about unsigned numbers. So this and this are just encodings of values, not in 2's complement encoding, but just really what we call the magnitude. So this is an interesting observation. So we basically have we can now start working on a circuit here that would implement x plus not y, and then detect a carry flag and be able to conclude that x is greater than y, and then we can actually revisit other cases where the x is less than y or equals to y. So we're sort of ready to get started. Basically, the plan is to build a circuit which will implement this addition and look at the carry flag of the result, and this would be our first step in building this 4-bit magnitude comparator device.